Well, we're going to talk about section 2.4. This is rectangular components. Most of the work in our statics course is when we are going to resolve our forces onto the XY grid, or when we get to 3 dimensions it'll be an XYZ grid. But let's say that we have a force X here and we have 2 axes Fx and Fy. We know that there's going to be components in the X direction and component in the Y direction. There'll be some angle theta. And we get to the resultant by, again, using the parallelogram approach, so drawing perpendicular or parallel lines from our components, and we can see that that's where the resultant would be, which would be the actual force. We can also use the triangle method. So let's say we have Fx and Fy, and here's going to be our angle theta. In both cases, whether we use the triangle method or the parallelogram method, we know that the component in the X direction is the cosine, because that's where the right triangle is. Right triangle is going to look right there. So the component in the X direction is the cosine, and the component in the Y direction would be the sine, or the side opposite. We know that the resultant, or the actual force, is the vector sum of Fx and Fy. Another thing to keep clear, however, is when the angle is defined with the x-axis like we just did, the sine and cosine look like that. If the force is defined with the y-axis, and we'll call that angle alpha, we'll still have a component in this direction, Fy, and a component in this direction, Fx. However, it's just important to note that the x component is going to be the opposite. Again, this is going to be the right triangle, or the right angle, so Fx is going to be the sine of alpha, and Fy will be the cosine of alpha. A couple of other methods that are very handy and very common. And let's say that we have a force here, and we have it, it's at some angle, but perhaps the angle isn't specified. We don't know what that angle is. However, we may have some other information based on the fact that maybe pointing up to a spot, maybe in space, look like that, and maybe that spot is specified. Let's say that it is 11 in the y direction and 10 in the x direction. So what we can know is that the angle can be determined, the angle theta can be determined, understanding that this is going to be the right triangle, that this would be the side opposite over the side adjacent. Pretty easy to see that the tangent of theta is equal to the side opposite over side adjacent, and then the angle, of course, can be determined using the inverse tangent of 11 over 10. Okay? Now another thing is that there are components of this force, we'll call that Fx and Fy. And here's the interesting thing, is that the force in this direction is related to the distance in this direction. The force in this direction is related to the distance in that direction. And all we have to do is just say that those are directly related, such that f of x is to 10 in the same way that f of y is to 11. And we can define either one of the, if we know one of the forces, we know the other force, then we can just say f of x is then equal to 10 elevenths of Fy. Another way, or another method, is what I call the slope method, and our textbook likes to use these little triangles like this to kind of help define what the direction of the force might be. Let's say that in this case, this little triangle looks like this: 3, 4, 5. Okay. We still, of course, have the angle force, or the force pointing up in that direction. You actually do not know what this angle is directly until you do just a little bit of work. But what we can know right off is that there are components of this force. We'll call that Fx and this Fy. And we can say that the force in this direction, in the x direction, is related to the distance of the little right triangle in that direction. Force in that direction is related to the distance, that distance in the right triangle. So let's just go ahead and write those down. We'll say Fx is to 4 in the same way that Fy is to 3, in the same way that the magnitude of the force is to 5. Again, obviously we can write a relationship between any two pieces of this little equation, such that Fx is equal to 4/3 of Fy. We can also find the angle, and we can know that the angle theta is related to those distances as well. So I'm just going to say that the angle theta is equal to the inverse tan of the side opposite over side adjacent, which is equal to the inverse sine of the side opposite over the hypotenuse, which is equal to the inverse cosine of the side adjacent over the hypotenuse. So all of those pieces can be put together to find out different components and different relationships that we might need. We will often use Cartesian vector notation when describing the forces. And this is very powerful and very easy, and we will use this probably more than anything else. So forces can be described as Cartesian vectors, and what we're saying there is that forces in the x direction can be said to be in the I direction. Forces in the y direction are going to be in the j direction. These are the same things. This is going to be the magnitude in the x direction, which we've already talked about, that being the magnitude, f cosine. The magnitude in the y direction is really the f sine. Again, those are going to be in the I direction and the j direction. If you write an equation with a vector on this side, then the other side has to be a vector as well. So both sides of this equation must be in vector form, and all this is just to say that I and j are shorthand for pointing in the x direction or pointing along the x-axis. Another thing to note, this may be obvious, but if you have a force pointing up here with some angle theta, and we may often write the components as well, fx and fy, just again, may be obvious, but don't add all three of those together. In other words, this description is equivalent to this. So we will maybe put them as different colors. What I like to do is put them in different colors so it's obvious that they're not all three there at the same time. Now, using Cartesian coordinate by using Cartesian coordinates, it makes it really easy to add vectors together. So here's just a little example. We'll just say that we have two forces here. We're going to call this F1 and F2. If we want to know where the resultant might be, that's again, we just draw, using our parallelogram approach, we're going to draw parallel lines here to our two forces. We should be able to recognize or know that the resultant is going to be pointing up in that direction at some angle. How do we find that direction and the angle that it's pointing at? Well, we can break the two forces up into their components, so let's just do that. We'll just say that there's going to be a force, if F1, let's say that it has a force in the x direction and a force in the y direction. And F2 will have a force in the x direction and a force in the y direction. Figuring out what those four components would be, then we know that the resultant in the x direction is going to be the sum of those two components in the x direction. So that would be minus f1 in the x plus f2 in the x. The reason that's a negative is because in this case it's pointing in the negative x direction, so we would put a negative sign in there when we find out the magnitude. We know that's in the x direction. The resultant in the y direction is going to be the resultant, or the component in the y direction plus the other component in the y direction. And then we look at the magnitude of the resultant. That's going to be pretty easy. We have the resultant is going to be there. It's going to have a resultant in the x and a resultant in the y. It'll have some angle theta here, and we can discover all that by just adding them together. So I'm going to say that the resultant is equal to Rx plus Ry. We know the magnitude. Another way of describing this would be R is equal to R mag at some angle theta, and where theta is equal to the inverse tan of Ry over x. And then the magnitude is determined by the square root of the sum of the squares. Anyway, when we put all that together, we can find out everything we need. We're looking for the angle and we're looking for the magnitude, we have to find the resultant components, or the resultants of the components, and then add them together in a vector sum. Alright, let's use this work now to find the resultant of a couple of these three forces. Let's say we have three forces here that are pulling on this bracket. Maybe pretty easy to see that the magnitude of the resultant is probably off in this direction, so I'm just going to draw it here. And I'm going to guess at an angle, or not a guess at the magnitude of the angle, but I'm going to guess at the kind of where the angle might sit, and I'll call that angle phi. What we're going to do is we're going to come up with the resultant, say that it is the sum of those three forces. So R equal to F1 plus F2 is F3. Again, those are three vectors on that side. It's pretty easy just to add them together. So I'm going to say that F1 is equal to, what we have is has a magnitude, and it has a component in this direction and a component in that direction. So that'll be 30 cos 45 in the I plus 30 sine 45 in the j direction. Now how about angle F2? F2 has a cosine component in that direction and a sine component in that direction. So let's just add it up. And I can just add them just like I would an arithmetic problem. 40 cos 15 I minus 40 sine 15. Okay. Again, it's negative in the y direction because it's pointing down. Our little triangle looks like that. Now how about F3? I'll say that that is equal to 25. It's positive, and this is going to be the sine component here in the I direction, minus 25 cos 15 in the j direction. You can add those three together just like an arithmetic problem, and I'll say that R is equal to 66.32 minus 13.29j. So I encourage you to always keep 4 significant digits as we're working through the problems. When you finally display the answer that might be required, then you can use 3 significant digits. But if you start using fewer than 4 or even 5 significant digits in your pre-work, you may get an answer that may not be as significant as you would like, or as the textbook might require. Anyway, so here is a vector description now of our resultant, which is good. That's a Cartesian vector description. Let's find out what the magnitude might be. Magnitude is going to be equal to the square root of Rx squared, which is 66.32 squared, minus, actually plus, a negative 13.29 squared. Now you can add this like this. In other words, understand that when you square a negative number, it will be a positive number. So what we get is the square root of that squared, square root, or plus the positive value when you square those two guys, and you get this is equal to 66.6 pounds. And then the theta, the angle theta, or excuse me, angle phi here, would be equal to the inverse tan of the side opposite, which would be the y component, over the side adjacent, which is the x component. And you get the angle is equal to 11.3 degrees. Anyway, so those are our 2 answers that we were looking for: the magnitude and the angle. And what I've defined here, this angle is a positive angle. I'm not going to really care whether it is a negative angle or a positive angle. If you drew it below the axis like this, then you have assumed that it is below the axis, and what we're looking for then, below the axis meaning it might be a negative angle in the way you might describe it, but we'll mostly be looking for the absolute value of these things. Well, here's a problem I'd like you to pause the video and work on for as long as it takes. But what we're looking for is to find out the unknown force here. There's an unknown force and an unknown angle phi that will result in a magnitude of a resultant right along the u-axis. So the resultant is going to be there, and it's given in the problem that its magnitude is 450, and the picture gives you the direction of 300. So use a similar process that we've just done. See if you can find out the unknown force 1 and the unknown phi. And then in a few minutes I'll walk through the solution. Okay, here's the solution for this. And again, we started with knowing that the resultant is on that axis, u, and it's in this direction, so there's going to be a component in the I direction, a component in the j direction. So I started by just defining that. F 450 cosine 30 in the I direction, 450 sine 30 in the j direction. You can multiply those out and you get the numbers. Recognize that F1 has a sine component in the x direction, cosine component in the y direction. Both the magnitude and the direction are unknown at this time. F2 is only in the x direction. F3 has a 5/13 component, so that's 5 over 13 in the x direction, and 12/13 component in the y direction. Again, that's going to be negative. Put those all together, we know that the resultant in the I direction is the sum of the forces in the x direction. The resultant in the j direction is the sum of the forces in the y direction. Put those together, you get two equations when you sum those together. How do you solve a two equations, two unknown problem like this? Well, it's pretty easy to divide the equations one from another, or divide one equation with the other one, and that's what I like to do. So I divided this equation with this equation, and you get an equation that looks like this. In that case, F1 is in both the numerator and denominator of that term, and sine over cosine is equal to the tangent, and then you can come up with this relationship to find the tangent of or find the actual angle, and then plugging that angle into either one of those equations, and you can find out the magnitude of the force. Again, here's the vector description of the force, and this is the final Cartesian vector description of F1 that we're looking for. So in this case, this would be the final answer, and that would be good. All right, a couple of things I just want to point out is things that are in the back of the book. You might look at Appendix A and look at the mathematical expressions and review. That would be helpful for you in terms of reviewing some trigonometry. Here's another page, which is just something that, again, go ahead and review. And then answers to selected problems. Many students fail to look in the back of the book to try to see these and to realize that they're there, but answers to some of the problems are in the back of the book, which you might see. And also not only the answers, but the solutions are available in the back of the book, or it's kind of partial solutions, I guess, for some of the fundamental problems. So anyway, I hope that helps you get started.